ये है मैग्नेटिज्म एंड मैटर। तो पहले इसका पीवाई को देख लेते हैं और फिर इसमें देखेंगे इसका एनसीईआरटी। तो ये है मैग्नेटिज्म एंड मैटर। इसमें सबसे पहला क्वेश्चन इसमें आया था वो है कि एनी फॉर्म कनेक्टिंग वायर ऑफ द लेंथ 12 MA and the 15 तार is bound up as a current I carrying coil in the shape and equal triangle of the phi day f square of the phi day the magnetic dipole moment of the coil in each case of the respectively है जो कितना हो जाएगा। तो दिए हुए है कि इसका हो जाएगा एरिया ऑफ मैग्नेटिक मोमेंट इक्वल टू क्या होता है। मैग्नेटिक मोमेंट इक्वल टू होता है मैग्नेटिक मोमेंट इक्वल टू क्या हो जाता है। तो गिवन क्या है लेंथ ऑफ द यूनिफॉर्म कनेक्टिंग बार एल इक्वल टू 12 है। रिफ्लेक्शन ऑफ यूनिफॉर्म कनेक्टिंग बार आर है। वी नो दैट मैग्नेटिक डाइपोल मोमेंट एम इक्वल टू एन आई ए होता है जहाँ आई द करंट इन द लूप है, ए द एरिया ऑफ द कॉइल है, एन ई द नंबर ऑफ द लूप है। तो केस वन में इक्वल ट्रायंगल ऑफ द फाइव है टोटल बार का लेंथ हो जाएगा एन इंटू पेरीमीटर ऑफ द ट्रायंगल। तो 12 है इक्वल टू एन इंटू 3 है तो एन कितना हो जाएगा 4। तो एरिया ऑफ द ट्रायंगल ए इक्वल टू √3/4 स्क्वायर। तो मैग्नेटिक डाइपोल मोमेंट एम इक्वल टू हो जाएगा एन आई ए। यहाँ से एम इज इक्वल टू हो जाएगा 4L इंटू √3/4 स्क्वायर। तो एम इज इक्वल टू हो जाएगा √3L ए स्क्वायर। स्क्वायर ऑफ द फाइव टोटल बार लेंथ एन इंटू पेरीमीटर ऑफ द स्क्वायर। तो 12A इंटू एन इंटू 4 है तो एन इज इक्वल टू 3 दिया हुआ है। तो एरिया ऑफ द स्क्वायर लूप हो जाएगा एन इज इक्वल टू स्मॉल स्क्वायर। मैग्नेटिक डाइपोल मोमेंट हो जाएगा एम इज इक्वल टू एन आई ए यानी एम इन 3 आई स्क्वायर। इसका आंसर क्या आ जाएगा ऑप्शन ए कि √3 आई स्क्वायर एंड 3 आई स्क्वायर इसका है जो आ जाएगा। नेक्स्ट है कि बार ऑफ द लेंथ एल मीटर कैरिंग ए करंट आई ऑफ 5 एम्पियर इवेंट इन द फॉर्म ऑफ ए सर्कल। तो इट्स मैग्नेटिक मोमेंट कितना हो जाएगा। तो एल इज इक्वल टू 2 पाई आर है तो आर इक्वल टू एल बाई 2 पाई हो जाएगा। तो मैग्नेटिक मोमेंट एम इज इक्वल टू आई है इंटू आई इंटू पाई आर स्क्वायर। तो आई इंटू पाई इंटू एल बाई 2 पाई के स्क्वायर तो आ जाएगा आई एल स्क्वायर बाई 4 पाई एम्पियर मीटर स्क्वायर। तो इसका आंसर आएगा डी आई एल स्क्वायर बाई 4 पाई एम्पियर मीटर स्क्वायर। नेक्स्ट है एयर हाई फोटो एंड इलेक्ट्रिकल कॉइल ऑफ द लेंथ 2.1 सेंटीमीटर एंड विथ 1.25 सेंटीमीटर कैरी ए करंट ऑफ 85 माइक्रो एम्पियर एंड सब्जेक्ट टू a magnetic field of strength 0.85 टेस्ला। वर्क डन फॉर द रोटेटिंग द कॉइल बाय 180 डिग्री अगेंस्ट द टॉर्क है जो कितना हो जाएगा। तो वर्क डन फॉर रोटेटिंग द कॉइल W इक्वल टू एम बी कॉस थीटा 1 माइनस कॉस थीटा 2 जहाँ पर थीटा 1 इक्वल टू 0 थीटा 2 इक्वल 80 डिग्री है। तो वर्क डन इक्वल टू एम बी कॉस 0 माइनस कॉस 180 यानी 2 MB यानी 2 NIA इंटू बी। अब वैल्यू पुट करेंगे तो 2 गुना 250 गुना 85 गुना 10⁻⁻6 गुना 2.1 गुना 1.25 गुना 10⁻⁴ गुना 0.85 तो आ जाएगा 9.5 गुना 10⁻⁶ जूल यानी 9.5 गुना 9.5 माइक्रो जूल। तो इसका आंसर जाएगा 9.5 माइक्रो जूल यानी 9.1 माइक्रो जूल। तो इसको कर सकते हैं कि ऑप्शन ए इसमें जो आंसर आ रहा है। नेक्स्ट है कि बार magnet is hung by a thin cotton thread in the uniform horizontal magnetic field and is in equilibrium state. The energy required to rotate it by 50 degree W. Now the torque required to keep the magnet in this position is तो W is equal to mb cos theta naught minus cos theta जहाँ m जो है magnetic moment of the magnet है तो B is equal to magnetic field और W is equal to mb cos 0 degree minus cos 50 degree यानी mb by 2 तो mb is equal to हो जाएगा 2W। तो torque on the magnet in this position is given by टॉर्क इज इक्वल टू एम क्रॉस पी यानी एम ई फाइन टू थीटा यानी 2W फाइन 50 डिग्री तो यानी W बाई √3 आ जाएगा। तो इसका आ जाएगा आंसर ऑप्शन बी √3W। नेक्स्ट है कि फॉलोइंग गिवन फिगर फॉर द अरेंजमेंट ऑफ ए बार मैग्नेट इन द डिफरेंट कॉन्फ़िगरेशन ईच मैग्नेट हैज मैग्नेटिक डाइपोल मोमेंट एम विच कॉन्फ़िगरेशन है द हाईएस्ट नेट मैग्नेटिक डाइपोल मोमेंट। तो मैग्नेटिक मोमेंट इज फ्रॉम शॉर्ट टू नॉर्थ एम नेट इज इक्वल टू एम स्क्वायर प्लस एम स्क्वायर प्लस 2m स्क्वायर कॉस थीटा वेयर एम नेट इज द मैक्सिमम इफ कॉस थीटा इज मैक्सिमम। तो कॉस थीटा विल मैक्सिमम व्हेन द थीटा विल मैक्सिमम तो एट थीटा बराबर 30 डिग्री एम नेट विल भी क्या हो जाएगा मैक्सिमम। आंसर ऑप्शन सी क्या हो जाएगा तीसरा कि थीटा जब मैक्सिमम होता है एम नेट विल मैक्सिमम कॉस थीटा इज मैक्सिमम सो कॉस थीटा मैक्सिमम व्हेन द थीटा विल भी मिनिमम होना चाहिए। तो ये तो 90 डिग्री है ये 180 डिग्री है 50 डिग्री तो मिनिमम किस में आता है इसमें तो आंसर जाएगा ऑप्शन सी। नेक्स्ट है a bar magnet of length L and the magnetic dipole moment M is bent in the form of an arc as shown in the figure. The net magnetic dipole moment कितना हो जाएगा तो इसमें आ जाता है कि the net magnetic moment M is equal to M into L जहाँ M pole length of strength है L जो है length of the magnet है। तो according to question I is equal to pi by 3 into R तो R is equal to 3I by pi। न्यू magnetic moment M dash equal to M into R होता है तो M into 3I by pi यानी 3 pi by into ML यानी 3M by pi। तो इसका आंसर आएगा ऑप्शन बी। इसका आंसर आएगा ऑप्शन बी 3M by pi। नेक्स्ट है कि कंपास नीडल विच इज अलाउड टू मूव इन हॉरिजॉन्टल प्लेन इज टेकन टू द magnetic pole. It will obtain the north south direction only. तो आंसर आएगा ऑप्शन सी. नेक्स्ट है कि बार मैग्नेट हैविंग a magnetic moment 2 गुना 10 power चार जूल per Tesla is free to rotate in the horizontal plane. A horizontal magnetic field B is equal to 6 गुना 10 power minus 4 Tesla exists in the space. The work done taking the magnetic slowly from the direction parallel to the field to direction 50 डिग्री from the field कितना हो जाएगा. तो वर्क डन इक्वल टू होता है एम बी कॉस थीटा वन माइनस कॉस थीटा टू, यानी थीटा वन 0 डिग्री थीटा टू बराबर 50 डिग्री. मैटिक मोमेंट एम इक्वल टू 2 गुना 10 पावर 4 जूल पर टेस्ला और बी इक्वल टू 6 गुना 10 पावर माइनस 10 टेस्ला. तो डब्ल्यू इक्वल टू एम बी 1 माइनस 1/2 यानी 6 जूल इसका आंसर आ रहा है. तो इसका आंसर कितना आ जाएगा 6 जूल, ऑप्शन सी. नेक्स्ट है ए चार्ज पार्टिकल चार्ज की हुई मूविंग इन द सर्कल ऑफ रेडियस आर विथ इन द फॉर्म ऑफ स्पीड वी. द फोर्फिटेड मैग्नेटिक मोमेंट म्यू इज गिवन बाय. तो एज रिवॉल्विंग चार्ज इज इक्वल टू ए करंट फॉर क्यू एफ इज इक्वल टू क्यू इंटू डब्ल्यू बाई 2 पाई. तो ओमेगा इज इक्वल टू वी बाई आर, where r is the radius of the circle and v is the uniform speed of the charge particle. Therefore, I is equal to qb by 2 pi r. तो mu is equal to I into a यानी I into pi r square. तो mu is equal to qb by 2 pi r into pi r square यानी 1 by 2 qb r. तो इसका आंसर आएगा 1 by 2 qb r, ऑप्शन ए. करंट अब इसका सही तरीका क्या है कि करंट पोटेंशियल टू सर्कुलर मोशन ऑफ ए चार्ज आई इक्वल टू क्यू बाई टू होता है. टी इक्वल टू पाई आर बाई बी, आई इक्वल टू क्यू बाई टू पाई आर इंटू भी. तो नो मैग्नेटिक मोमेंट म्यू गिवन बाई म्यू इक्वल टू आई इंटू ए. सो म्यू इक्वल टू क्यू भी बाई टू पाई आर इंटू पाई आर स्क्वायर. तो म्यू इक्वल टू क्यू भी आर बाई टू. तो आंसर आएगा क्यू भी आर बाई टू. अगला क्वेश्चन, ए बार मैग्नेट ऑफ मैग्नेटिक मोमेंटम इज प्लेस्ड इन द मैग्नेटिक फील्ड ऑफ डायरेक्शन बी. द टॉर्क एक्सर्टेड ऑन इट कितना. टॉर्क इक्वल टू एम क्रॉस बी, आंसर सी डायरेक्ट. अब अर्थ मैग्नेटिज्म का चैप्टर, अर्थ मैग्नेटिज्म का जो टॉपिक है वो तो है ही नहीं, तो ये नहीं है. टोटल क्वेश्चन ही अर्थ मैग्नेटिज्म का नहीं है इसमें, तो अर्थ मैग्नेटिज्म तो नहीं देख रहे हैं. तो अब देखते हैं जिससे क्वेश्चन आते हैं वो है मैग्नेटिक मटेरियल्स. तो एन आयरन रोड ऑफ सस्पेक्टिबिलिटी 599 में इज सब्जेक्टेड टू ए मैग्नेटाइजिंग फील्ड ऑफ द 1200 एम्पियर पर मीटर. द परमिटिविटी ऑफ द मटेरियल ऑफ द रॉड है जो कितना हो जाएगा. वी नॉट के वैल्यू ले सकते हैं 4 पाई गुना 10 पावर माइनस 7 टेस्ला मीटर पर एम्पियर. तो गिवन सस्पेक्टिविटी काई 599 है. मैग्नेटिक फील्ड है जो 1200 एम्पियर पर मीटर है. परमिटिविटी ऑफ द मटेरियल ऑफ द रॉड म्यू एम इक्वल टू म्यू नॉट 1 प्लस काई यानी 2.4 पाई इंटू 10 पावर माइनस 4 टेस्ला मीटर पर एम्पियर. तो इसका आंसर आएगा ऑप्शन डी 2.4 पाई इंटू 10 पावर माइनस 4 टेस्ला मीटर पर एम्पियर. नेक्स्ट है ए थिन डायमैग्नेटिक रॉड प्लेस्ड वर्टिकली बिटवीन द पोल्स ऑफ इलेक्ट्रोमैग्नेट. व्हेन द करंट इन द इलेक्ट्रोमैग्नेट इज स्विच्ड ऑन द डायमैग्नेटिक रॉड इज पुश्ड अप out of the horizontal magnetic field, hence the rod against gravitational potential energy. The work required to do this comes from the C of current force है जो आता है. तो ऑप्शन सी हो जाएगा. As the force of the current is switched on, a magnetic field set up in between the poles of the electromagnet. As we know that a diamagnetic substance when placed in a magnetic field acquires a visual magnetic opposite to the direction of the magnetic field. Also in the presence of the field non-uniform, these substances are attracted towards the bigger field. That means they move from the stronger to the bigger magnetic field. Due to the region, the rod is deprived by the field produced to the current force, hence it is pushed up out of the horizontal field and against the gravitational potential energy. अगला क्वेश्चन, द मैग्नेटिक सस्पेक्टिविटी नेगेटिव किसके लिए होता है. तो डी डायमैग्नेटिक मटेरियल के लिए है जो नेगेटिव होता है ओनली. तो एज वी नो द रिलेशन बिटवीन द मैग्नेटिक परमिटिविटी एंड द सस्पेक्टिविटी ऑफ द मटेरियल इज म्यू आर इक्वल टू 1 प्लस काई एम. फॉर द डायमैग्नेटिक मटेरियल्स म्यू आर जो होता है लेस देन 1 होता है. सो अकॉर्डिंग टू द इक्वेशन द मैग्नेटिक सस्पेक्टिविटी काई एम ऑफ द डायमैग्नेटिक सब्सटेंस विल बी नेगेटिव. While in the case of the para and ferromagnnetic substance diamagnetic susceptibility क्या होता है पॉजिटिव. तो इसका आंसर आएगा ऑप्शन डी. अगला सवाल, अगला सवाल है देयर फोर लाइट बेट रॉड सैंपल्स ए बी सी एंड डी सेपरेटेड suspended by the thread. A bar magnet is slowly brought near the each sample and following observations are noted. If A is feebly repelled, B is feebly attracted, C is strongly attracted, D remains unaffected. Which one of the following is true? The answer आएगा D कि B is of the paramagnetic material. So paramagnetic materials will be feebly attracted, diamagnetic material will be feebly repelled, and the ferromagnetic material will be strongly attracted. The answer is option D. Next, if a diamagnetic substance is brought near the north or the south pole of a paramagnet, तो it is क्या हो जाएगा repelled by both the poles. So diamagnetic substances are weakly magnetized in a direction opposite to the that of the applied magnetic field. These are repelled in external magnetic field. That means have a tendency to move from the high to low field region. That means it is repelled by north and south poles of the bar magnet. Next है कि nickel show the ferromagnetic property at room temperature. If the temperature increases beyond Curie temperature, then it will show. The answer आएगा option A paramagnetism. Nickel exhibits ferromagnetism because of the quantum physical effect called exchange coupling, in which the electron spin of the one atom interact with those of the neighboring atoms. The result is alignment of the magnetic dipole moment of the atoms in spite of their randomizing tendency of the atomic collision. This persistent alignment is what gives ferromagnetic materials their magnetism. If the temperature of the ferromatic material is above the certain critical value called the Curie temperature, the exchange coupling is to be effective. Most such materials become simply paramagnetic, that means the dipoles will still tend to align with an external field, but much more weakly, and thermal agitation can now more easily disrupt the alignment. फिर है कि above Curie temperature क्या होता है, ferromatic substance becomes the paramagnetic. The ferromagnetism decays with rising temperature. If we heat a ferromatic substance, then at a different temperature, the ferromagnetism property of the substance suddenly disappear and the substance become paramagnetic. The temperature above which a ferromatic substance becomes paramagnetic is called the Curie temperature of the substance. अगला सवाल, if the magnetic dipole moment of the an atom of a diamagnetic material paramagnetic material and the ferromatic material are denoted by mu d, mu p and mu f respectively, then answer is option C, mu d is equal to 0, mu p is not equal to 0. In diametric substance, in each pair of electrons, the spin of both the electrons are in the opposite direction, hence the electrons of each pair completely cancel the magnetic moment of each other. Thus the net magnetic moment by each atom of the such substance is 0, यानी mu d is equal to हो जाएगा 0. The property of the paramagnetism is bound in those substances whose atom or molecules have an excess of the electrons spinning in the same direction. Hence, atom of the paramagnetic substance have the permanent magnetic moment mu p is not equal to 0. The property of the ferromagnetism is found in the substance which acquire very strong magnetism when placed in an external magnetic field. Like the paramagnetic substances, each atom of the ferromagnetism substance also has a permanent magnetic moment, that means mu f is not equal to 0. अगला सवाल कि according to the Curie law, the magnetic susceptibility of a paramagnetic substance at an absolute temperature T is proportional to. So according to the Curie law, magnetic susceptibility of a paramagnetic substance is inversely proportional to the absolute temperature. Chi m inversely proportional to 1 by T. तो आंसर जाएगा ऑप्शन सी. नेक्स्ट है, ए डायमेटिक मटेरियल इन मैग्नेटिक फील्ड मूव्स, तो इसका आंसर जाएगा सी, फ्रॉम द स्ट्रॉन्गर टू द बिगर पार्ट्स ऑफ द फील्ड. When a diamagnetic material is placed in an external magnetic field, the spin moment of the electrons is so modified that electrons which produce the magnetic moment in the directions of the external field slow down, while electrons which produce the magnetic moments in the opposite direction get accelerated. The net magnetic moment is induced in the opposite direction of the applied magnetic field, hence the substance is magnetized opposite to the external field. The field moves from the stronger to the bigger parts of the magnetic field. Diamagnetism is present in all of the substance, however its effect is so big in most cases that it gets shifted by the other effects like the paramagnetism, ferromagnetism, etc. अगला सवाल, in which type of the material the magnetic susceptibility does not depend on the temperature, and the option A, diamagnetic. तो इसमें आता है ऑप्शन ए कि द मैग्नेटिक सस्पेक्टिविटी ऑफ ए मटेरियल इज मेजर ऑफ द इज विथ विच स्पेसिमेन ऑफ द मटेरियल कैन बी मैग्नेटाइज इन द मैग्नेटिक फील्ड. फॉर ए डायमेटिक सब्सटेंस मैग्नेटिक सस्पेक्टिविटी इज इंडिपेंडेंट ऑफ द टेम्परेचर. नेक्स्ट है, ए डायमेटिक सब्सटेंस इज ब्रॉट नियर स्ट्रॉन्ग मैग्नेट देन इट इज, तो इसका आंसर आएगा रिपेलेड बाय द मैग्नेट. तो when a diametric substance are placed in the magnetic field of a strong magnet, then it is feebly magnetized in the opposite direction of the field, or it is repelled by a strong magnet. Next, protecting a sensitive equipment from the external magnetic field, it should be, तो आंसर है सी, आंसर होगा बी, placed inside an iron can. तो iron is a ferromagnnetic substance. There are no magnetic lines of the force inside a ferromagnnetic substance, so equipment may be protected by placing it inside the can made of a ferromagnnetic substance and it is placed inside an iron can. तो यहाँ पर इसका पीवाई क्यों होता है, अब देखेंगे मैग्नेटिज्म एंड मैटर का एनसीईआरटी. इस चैप्टर से तो आ ही सकता है स्टेटमेंट वाले क्वेश्चन, तो इसको तो ध्यान से देखना है. तो मैग्नेटिक इसमें आता है कि magnetic phenomena are universal in the nature. Vast distant galaxy, the tiny visual atoms, humans, and the beasts all are permitted through a host of the magnetic fields probability of the forces. The Earth's magnetism predates human evolution. The word magnet is derived from the nature of an island in Greece called Magnesia, where ore deposited were found as early as 600 BC. In the previous chapter, we have learned that the moving charge or the electric current produce magnetic field. This discovery, which was made in the early part of the 19th century, credited to the Oersted, Ampere, Biot, and the Savart, among others. In the present chapter, we take a look at the magnetism as a subject in this on that some of the commonly known ideas regarding magnetism are: the Earth behaves as a magnet with the magnetic field pointing approximately from the geographic south to the north. When the bar magnet is feebly suspended, it points in the north-south direction. The tip which points to the geographic north is called the north pole, and the tip which points to the geographic south is called the south pole of the magnet. फिर आता है कि there is repulsive force when north poles or the south poles of the two magnets are brought close together. Conversely, there is attractive force between the north pole of the one magnet and the south pole of the other. We cannot exclude the earth or the south pole of a magnet. If a bar magnet is broken down into halves, we get two similar bar magnets with somewhat bigger property. Unlike electric charge, isolated magnetic north and the south poles known as the magnetic monopoles do not exist. It is possible to make magnets out of the iron and its alloy. We begin with a description of the bar magnet and its behavior in an external magnetic field. We describe Gauss law of magnetism. We next describe how materials can be classified on the basis of their magnetic property. We describe the para, di, and the ferromagnetism. फिर आता है the bar magnet. We begin our study by examining iron fillings sprinkled on a sheet of the glass placed over a short bar magnet. The arrangement of iron fillings is shown in figure 5.1. The pattern of the iron filling suggests that the magnet has two poles similar to the positive and the negative charge of an electric dipole. As mentioned in the introductory section, one pole is directed at the north pole and the other south pole when suspended freely. These poles point approximately towards the geographic north and the south poles respectively. A similar pattern of the iron filling is observed around a current carrying solenoid. यहाँ पर the arrangement of the iron filling surrounding a bar magnet. The patterns mimics magnetic field lines. The pattern suggests that the bar magnet is a magnetic dipole. फिर आता है the magnetic field lines. तो the pattern of the iron filling permits us to plot the magnetic field lines. This is shown both for the bar magnet and the current carrying solenoid. For comparison, refer to chapter 1, figure 1.1 for the electric field lines of an electric dipole are also displayed. In figure 5.2c, the magnetic field lines are a visual and initiative relation of the magnetic field. The properties are the magnetic field lines of a magnet or the solenoid form the continuous closed loop. This is unlike the electric dipole where these field lines begin from a positive charge and end on a negative charge or escape to the infinity. अब यहाँ पर दिया हुआ है the field lines a bar magnet, the current carrying finite solenoid and the electric dipole a large distance. The field lines are very similar. The curves labeled 1 and 2 are closed Gaussian surfaces. फिर यहाँ पर दिया हुआ है a calculation of the actual field of a finite solenoid in order to demonstrate it similar to that of the bar magnet. A magnetic needle is a uniform magnetic field. The arrangement may be used to determine either B or the magnetic moment M of the needle. फिर आता है the tangent to the field at a given point represents the direction of the net magnetic field B at that point. The larger number of the field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. In figure 5.2a, B is larger around region 2 than in the region 1. The magnetic field lines do not intersect, but if they did, the directions of the magnetic field would not be unique at the point of the intersection. One can plot the magnetic field lines in a variety of the ways. One way is to place a small magnetic compass needle at the various positions and note its orientation. This gives us an idea of the magnetic field direction at various points in the space. फिर आता है bar magnet as an equivalent solenoid. So in the previous chapter, we have explained how a current loop acts as a magnetic dipole. We mentioned Ampere's hypothesis that all magnetic phenomena can be explained in the terms of the circulating currents. The resemblance of the magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought of as a large number of the circulating currents in analogy with a solenoid. Cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with a bigger magnetic property. The field lines remain continuous, emerging from the one face of the solenoid and entering into the other face. One can test this analogy by moving a small compass needle in the neighborhood of a bar magnet and a current carrying flat solenoid and noting that the deflection of the needle are similar in both cases. To make this analogy more firm, we may calculate the axial field of a finite solenoid depicted. We can demonstrate that at large distances, this axial field resembles that of a bar magnet. The magnitude of the field at point P due to the solenoid is B is equal to mu naught over 4 pi 2m by RQ. This is also for axial magnetic field of a bar magnet which one may obtain experimentally. Thus, a bar magnet and a solenoid produce similar magnetic field. The magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. फिर आता है the dipole in the uniform magnetic field. So let us place a small compass needle of the non-magnetic moment M, allowing it to oscillate in the magnetic field. This arrangement is shown in the figure 5.3b. The torque on the needle is tau equal to m cross b. In the magnitude, tau equal to mb sine theta. Here tau is storing torque and theta is the angle between m and b. An expression for the magnetic potential energy can be obtained on the line similar to the electrostatic potential energy. The magnetic potential energy m is given by m is equal to tau theta d theta यानी mb sin theta d theta minus mb cos theta यानी minus m dot p. We have emphasized in chapter 2 that the zero of the potential energy can be fixed at one's convenience. Taking the constant for the integration to be 0 means fixing the zero of a potential energy at theta equal to 90 degree. That means when the needle is perpendicular to the field, equation 5.3 shows that the potential energy is minimum minus mb at 0 degree most stable position and maximum plus mb at theta equal to 180 degree most unstable position. Next है कि what happens if a bar magnet is cut into two pieces transverse to the length and along its length. तो और अगला क्वेश्चन है मैग्नेटाइज नीडल इन यूनिफॉर्म मैग्नेटिक फील्ड एक्सपेरियंस a torque about no but no net force. An iron nail near a bar magnet however experiences a force of attraction in addition to a torque. Why? और उसके बाद फिर आता है must every magnetic configuration have a north pole and a south pole. What about the field due to a toroid? Two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. We do not know which one. How would one ascertain whether or not both are magnetized? If one is magnetized, how does one certain which one? उसके बाद फिर आता है in either case one gets two magnets each with a north and a south pole. No force if the field is uniform. The iron nails experience a non-uniform field due to a bar magnet. There is induced magnetic moment in the nail, therefore it experiences both force and the torque. The net force is attractive because the induced south pole, say in the nail, is closer to the north pole of the magnet than the induced north pole. Not necessarily true only if the force of the field has a net non-zero magnetic moment. This is not so for the toroid or even for the straight infinite conductor. Try to bring different ends of the bar of closure. A repulsive force in some situation establishes that both are magnetized. If it is always attractive, then one of them is not magnetized. If in a bar magnet, the intensity of the magnetic field is the strongest at the two ends poles and the biggest at the frontal region. This fact may be used to determine whether A or B is the magnet. In this case, to see which one of the two bars is a magnet, pick up one say and lower of its wind first on one of the end of the other say and then on the middle of the B. If you notice that in the middle of the B A experiences no force, then B is magnetized. If you do not notice any change from the end of the middle of the B, then A is magnetized. फिर आता है the electrostatic analog. तो comparison of equation 5.1, 5.2, 5.3 with the corresponding equation of the electric dipole suggests that magnetic field at large distance due to a bar magnet of magnetic moment M can be obtained from the equations of the electric field due to electric dipole of the dipole moment P by making the following placement. E जो है वो B के जैसा है, P जो है M के जैसा है, 1/4 pi naught है, mu naught 4 के जैसा है. In particular, we can write down the equatorial field B of a bar magnet at a distance r for r much greater than L, where L is the size of the magnet. So B is equal to minus mu naught by M 4 pi by r cube. Like by the axial field BA for the bar magnet r is much greater than L is B is equal to mu naught of 4 pi 2M by r cube. So equation 5.5 is just equation 5.1 in the vector form. Table 5.1 summarizes the analogy between electric and the magnetic dipoles. फिर यहाँ पर दिया हुआ है कंपेरिजन. तो डायपोल मोमेंट P 1/0 म्यू नॉट के जैसा है और P जो है M के जैसा है. इक्वेटोरियल फील्ड फॉर द फर्स्ट डायपोल -P/4 pi naught r cube minus mu naught M/4 pi r cube. Axial field for the fourth dipole 2P/4 pi naught r cube और mu naught 2M/4 pi r cube. एक्सटर्नल जो फील्ड है टॉर्क P क्रॉस E और M क्रॉस B और एक्सटर्नल फील्ड एनर्जी जो है -P डॉट E और -M डॉट B जैसा है. अब यहाँ पर है कि Figure 5.4 shows a small magnetized needle P placed at a point O. The arrows show the directions of its magnetic moment. The other arrows show different position and the orientations of the magnetic moment and other identical magnetized needle Q. In which configuration the system is not in equilibrium? In which configuration is the system in the stable and the unstable equilibrium? Which configuration corresponds to the lowest potential energy among all the configurations shown? The potential energy of the configuration arise due to the potential energy of the one dipole, say Q in the magnetic field due to the other P. U the real that the field due to the P is by the expression. So Bp is equal to minus mu naught of 4 pi mp by rq on the normal bisector or Bp is equal to mu naught of 4 pi 2 mp by rq on the axis, where mp the magnetic moment of the dipole P. Equilibrium is stable when mq is parallel to the Bp and unstable when it is anti-parallel to the Bp. फिर आता है कि for instance the configuration Q3 for which the Q is along the perpendicular bisector of the dipole P, the magnetic moment of Q is parallel to the magnetic field at position 3 and Q3 is stable. Thus PQ1 and the PQ2 और दूसरा जाएगा PQ and the PQ6 stable होगा, PQ5 PQ4 unstable होगा, फिर इसमें आएगा PQ6. अब है magnetism and the Gauss law. So in the chapter 1 we have studied the Gauss law for the electrostatic. In the figure 5.2 see that for a closed surface represented by the 1, the number of the lines leaving the surface is equal to the number of the lines entering it. This is consistent with the fact that no net charge is included by the surface. However, in the same figure, for the closed surface, there is a net outward flux, so they not include a net positive charge. The situation is radically different for magnetic fields which are continuous and form the closed loop. Examine the Gaussian surface represented by the 1 or 2 in the figure 5.2a or figure 5.2b. Both cases visually demonstrate that the number of the magnetic field lines leaving the surface is balanced by the number of the ellipse lines entering it. The net magnetic flux is 0 for both the surface. This is true for any closed surface. फिर यहाँ पर दिया हुआ है कि consider a small vector area element delta f for a closed surface f as in the figure 5.5. The magnetic flux through delta is defined as the phi b is equal to b dot delta f, where b is the field delta at delta f. We divide f into many small area elements and calculate the individual flux through each. Then the net flux phi b is equal to sigma b dot delta f equal to 0, where all f stands for all area elements delta f. Compare this with the Gauss law of the electrostatic. The flux through a closed surface in that case is given by E dot delta f equal to q by E naught, where q is the electric charge enclosed by the surface. The difference between the Gauss law for the magnetism and that for the electrostatic is reflection to the fact that isolated magnetic poles, also called monopoles, are not known to exist. There are no forces or the things of B. The simplest magnetic element is a dipole or a current loop. All magnetic phenomena can be explained in terms of the arrangement of the dipoles and or the current loops. The Gauss law for the magnetism is the net magnetic flux through any closed surface is 0. उसके बाद फिर आता है कि many of the diagrams given in the figure 5.6 for the magnetic field lines, thick lines in the figure, wrongly pointed out part is the wrong with them. Some of them describe electrostatic field lines correctly. Point out which one. फिर A है, B है, A है, B है, C है, D है, E है और F है और फिर G है. तो पहला जो है वो wrong है. क्यों? क्योंकि magnetic field lines can never emanate from a point as shown in the figure over any closed surface. The net flux of the B must always be 0. That means pictorially, as many field lines should seem to enter the same as the number of the lines leaving it. The field lines shown in fact represent electric field of a long positively charged wire. The correct magnetic field lines are encircling the straight connector as described in the chapter 4. फिर बी वाला देखें जो एम्प्टी उसमें है तो ये भी रॉन्ग है. क्यों? क्योंकि magnetic field lines like the electric field lines can never cross each other because otherwise the directions of the field at a point of the intersection is ambiguous. There is further error in the figure. Magnetostatic field lines can never form closed loops around the empty space. A closed loop of the static magnetic field line must enclose a region across which a current is passing. By contrast, electrostatic field lines can never form the closed loop neither in the empty space nor when the loop encloses the charge. और सी की बात करें तो ये राइट है. सी वाला है जो सही है क्योंकि magnetic lines are completely confined within a toroid. Nothing wrong here in the field lines forming closed loop since each loop encloses a region across which a current passes. Not for the clarity of the figure, only a few field lines with the toroid have been shown. Actually, the entire region enclosed by the buildings contains the magnetic field. और चौथा देखें तो ये है जो डी जो है ये है जो wrong है क्योंकि field lines due to the solenoid at its ends and outside cannot be so completely straight and confined. Such a thing violates Ampere's law. These lines should curve out both ends and meet eventually to form the closed loop. तो उसके बाद जो E वाला है ये है जो right है. These are field lines outside inside a bar magnet. Note carefully direction for the field lines inside. Not all the field lines emanate out of north pole. Around both the north pole and the south pole, the net flux of the field क्या हो जाएगा 0 हो जाएगा. फिर F जो है ये है wrong है क्योंकि these field lines cannot properly represent a magnetic field. Look at the upper region. All the field lines seem to emanate out of the faded plate. The net flux to the surface surrounding the faded plate is not 0. This is impossible for a magnetic field. The given field lines, in fact, for the electrostatic field lines around a positively charged upper plate and negatively charged lower plate. The difference between the figure 5.6 E and F should be carefully grasped. फिर जो G है EF और G जो है वो wrong है क्योंकि magnetic field lines between the two pole cannot be precisely straight at ends. Some fringing in the lines is inevitable. Otherwise, Ampere's law is violated. This is also true for the electric field lines. फिर इसके बाद अगला क्वेश्चन है magnetic field lines can show the directions at every point along which the small magnetic needle aligns at that point. Do the magnetic field lines also represent the lines of the force on the moving charge particle at every point? If magnetic monopole exists, how would the Gauss law of magnetism be modified? Does a bar magnet exert torque on itself due to its own field? Does one element of a current-carrying bar exert a force on another element of the same bar? फिर magnetic field lines are due to charge in the motion. Can the system have a magnetic moment even though its net charge is 0? तो पहला क्वेश्चन था कि magnetic field lines for the directions at every point along which a small magnetic needle aligns at the point. Do the magnetic field lines also represent the lines of the force on moving charge particle at every point? तो no, the magnetic force is always normal to the B. Remember, magnetic force QBB it is misleading to call magnetic field lines as the lines of the force. फिर है कि if a magnetic monopole existed, how would the Gauss law of the magnetism be modified? तो गॉस लॉ ऑफ द मैग्नेटिज्म स्टेट्स दैट द फ्लक्स B through any closed surface is always zero, यानी सिग्मा B delta F is equal to zero. If monopole gives the right hand side would be equal to the monopole magnetic charge QM enclosed by the F, analogous to the Gauss law is electrostatic. B delta F mu not QM, where QM is the monopole magnetic charge enclosed by the F. फिर उसके बाद दिया हुआ है कि does a bar magnet a torque on itself due to its own field? Does one element of a current carrying by for the force on another element of the same bar? तो इसका आंसर है कि नो, देयर इज नो टॉर्क फोर्स फॉर द टॉर्क ऑन एलिमेंट ड्यू टू द फील्ड प्रोड्यूस्ड by that element itself, but there is a force for a torque on an element of the same bar. For the specific force straight bar, the force is zero. फिर एक magnetic field line rise due to charge in the motion. Can the system have magnetic moments even though its net charge is zero? तो yes, the average of the charge in the system may be zero, yet the mean of the magnetic moment due to the various current loops may not be zero. We will come across such example in connection with the paramagnetic material where atoms have net dipole moment through their net charge is zero. अब बात करते हैं मैग्नेटाइजेशन एंड मैग्नेटिक इंटेंसिटी की. तो द अर्थ abounds with a bewildering variety of elements and the compounds. In addition, we will look by we have been synthesizing a new large compounds and even elements. One would like to classify the magnetic property of these substances. In the present section, we define and explain certain terms which will help us to carry out the exercise. We have seen that the circulating electrons in an atom has a magnetic moment. In a bulk material, these moments add up vectorially and they can give a net magnetic moment which is non-zero. We define the magnetization M of a sample to be equal to its net magnetic moment per unit volume. M is equal to M net by V. M is a vector with dimension L inverse A and is measured in the unit of the ampere per meter. Consider a long solenoid of the n turns per unit length and carrying a current I. The magnetic field in the interior of the solenoid is found to be given by the B naught equal to mu naught Ni. If the interior of the solenoid is filled with material with non-zero magnetization, the field inside the solenoid will be greater than the B naught. The net field B in the interior of the solenoid may be expressed as B is equal to B naught plus Bm. और इसके बाद फिर आता है where Bm is the field contributed by the material's core. It turns out that this additional field Bm is proportional to the magnetization M of the material and is specified as Bm is equal to mu naught M, where mu naught is the same constant permittivity of the vacuum that appears from the Barth-Savart law. It is convenient to introduce another vector field H called the magnetic intensity, which is defined by H is equal to B by mu naught minus M, where H has the same dimension and M is measured in units of ampere per meter. Thus, the total magnetic field B is written as B is equal to mu naught H plus M. We repeat our finding. We have partitioned the contribution of the total magnetic field inside the sample into two parts, one due to the external factors such as the current in the solenoid. This is represented by the H. The other is due to the specific nature of the magnetic material, namely H. The latter quantity can be influenced by the external factors. This influence is materially specified M is equal to chi into H, where chi, a dimensionless quantity, appropriately called the magnetic susceptibility. It is a measure of how a magnetic material responds to an external field. Chi is small and positive for the materials which are called paramagnetic. It is small and negative for the materials which are termed diamagnetic. In the latter case, M and H are in direction. From equation 5.1 to 5.3, we have B is equal to mu naught 1 plus chi into H. So mu into mu r into H, mu into H, where mu r is equal to 1 plus chi is a dimensionless quantity called the relative magnetic permittivity of the substance. It is analog of the dielectric constant in electrostatic. The magnetic permittivity of the substance is mu and it has the same dimension as an unit as the mu naught. So mu is equal to mu naught into mu r, mu naught 1 plus chi. The three quantities chi, mu r and mu are integrated and one of them is interdependent. Given one, the other two may be easily determined. फिर है कि a solenoid has a core of the material with relative permittivity charge for the buildings of the solenoid are insulated from the core and carry a current of 2 ampere. If the number of turns is 1000 per meter, calculate the H, M and B and the magnetizing current IM. तो इसमें दिया हुआ है the field H is dependent on the material of the core and H is equal to Ni, यानी कि 1000 गुना 2.0 2 गुना 10 का पावर 3 एम्पियर पर मीटर. The magnetic field B given by B is equal to mu r mu naught into H, यानी 400 गुना 4 गुना 10 का पावर माइनस 7 गुना 2 गुना 10 का पावर 3 एम्पियर पर मीटर, यानी 1 टेस्ला. और मैग्नेटाइजेशन गिवन बाय बी एम इज इक्वल टू बी माइनस म्यू नॉट बाई एच बाई म्यू नॉट, यानी म्यू आर म्यू नॉट माइनस इंटू एच माइनस म्यू नॉट बाई एच बाई म्यू नॉट. तो यहाँ से आ जाएगा 8 इंटू 10 का पावर 5 एम्पियर मीटर. The magnetizing current IM is the additional current that needs to be passed through the buildings of the solenoid in the absence of the core, which would give B value at the presence of the core. Thus B is equal to mu Rn I plus Im. Thus I is equal to A, B is equal to 1 plus B get Im is equal to 794 एम्पियर. अब बात करते हैं मैग्नेटिक प्रॉपर्टी ऑफ द मटेरियल्स की। तो द डिस्कशन इन द प्रीवियस सेक्शन will help us to classify materials for the magnetic, paramagnetic, diamagnetic or ferromagnetic. In terms of the susceptibility, chi, a material is diamagnetic, small, and ferromagnetic if chi is large and positive. A glance at the table 5.2 gives one a better feeling for these materials where each of a small positive and number introduced to quantify paramagnetic materials. Next we describe these materials in some detail. तो डायमैग्नेटिक होता है और इससे क्वेश्चन पूछे भी गए थे। तो डायमैग्नेटिक होता है -1 काई और 0 के बीच में, काई जो होता है -1 और 0 के बीच में होता है। अब यहाँ पर है जो करके पूछ सकता है। फिर म्यू आर जो होता है 0 और 1 के बीच में होता है, और म्यू जो होता है म्यू नॉट से छोटा होता है। पैरामैग्नेटिक का जो होता है काई 0 और ई के बीच में होता है, म्यू आर 1 और 1 + ई के बीच में होता है, और म्यू जो होता है ग्रेटर देन म्यू नॉट होता है। फेरोमैग्नेटिक का काई ग्रेटर मच ग्रेटर देन होता है, म्यू आर भी मच ग्रेटर देन होता है, और म्यू भी मच ग्रेटर देन म्यू नॉट हो जाता है। तो यहाँ पर बिहेवियर ऑफ द मैग्नेटिक फील्ड लाइन्स नियर ए डायमैग्नेटिक पैरामैग्नेटिक सब्सटेंस जो दिखाए हुए, ये नियर द डायमैग्नेटिक और ये नियर द पैरामैग्नेटिक सब्सटेंस दिखाए हुए। फिर आता है डायमैग्नेटिज्म। तो डायमैग्नेटिक सब्सटेंस इसमें दिखाता है कि डायमैग्नेटिक सब्सटेंस आर दोज व्हिच हैव टेंडेंसी टू मूव फ्रॉम द स्ट्रॉन्गर टू द बिगर पार्ट्स ऑफ द इलेक्ट्रिक magnetic field. In other words, unlike the way a magnet attracts metal like the iron, it would repel a diamagnetic substance. Figure 5.1 shows a bar of a diamagnetic material placed in an external magnetic field. The field lines are repelled or expelled, and the field inside the material is reduced. In most cases, this direction is flat, being the part of the discovered patch. When placed in a non-uniform magnetic field, the bar will tend to move from the high to the low field. फिर है कि द सिंपलेस्ट एक्सप्लेनेशन फॉर द डायमैग्नेटिज्म इज एज फॉलो। इलेक्ट्रॉन्स इन एटम ऑर्बिटिंग अराउंड न्यूक्लियस possess orbital angular momentum. These orbiting electrons are equivalent to the current carrying loop and thus possess orbital magnetic moment. Diamagnetic substances are the one in which the resultant magnetic moment is in an atom is zero. When magnetic field is applied, those electrons having the orbital magnetic moment in the same direction slow down, and those in the opposite direction speed up. This happens due to the induced current in accordance with the Lenz's law, which you will study in the chapter 6. The substance develops a net magnetic moment in the direction opposite to that of the applied field, and hence repulsion. Some diamagnetic materials are bismuth, copper, lead, silicon, nitrogen at the FTP, water, and sodium chloride. Diamagnetism is present in all the substances. However, the effect is so big in most cases that it gets shifted by other effects like the paramagnetism, ferromagnetism, etc. The most exotic diamagnetic materials are the superconductors. These are metals cooled to a very low temperature, which gives both perfect conductivity and the perfect diamagnetism. Here the field lines are completely expelled. Chi is equal to -1, mu are equal to 0. A superconductor repels a magnet, and by Newton's third law is repelled by the magnet. The phenomena of the perfect diamagnetism in the superconductor is called the Meissner effect, after the name of the discoverer. Superconductor's magnet can be gainfully exploited in a variety of the situations, for example, for running magnetically leviated superfast train. फिर आता है पैरामैग्नेटिज्म। तो पैरामैग्नेटिक सब्सटेंसेज आर दोज which get quickly magnetized when placed in the free magnetic field. They have tendency to move from a region of the bigger magnetic field to a strong magnetic field. They get quickly attracted to a magnet. The individual atoms or the ions or molecules of a paramagnetic material possess a permanent magnetic dipole moment of their own. On account of the serious random motion, thermal motion of the atom, no net magnetization is seen. In the presence of the external field B naught, which is strong enough and at low temperature, the individual atomic dipole moment can be eliminated to a larger and point in the same direction as B naught. Figure 5.1 b shows a bar of the paramagnetic material placed in a external field. The field lines gets concentrated inside the material, and the field inside is enhanced. In most cases, the enhancement is slight, being 1 part of the 10^5. When placed in a non-uniform magnetic field, the bar will tend to move from the big field to the strong. पे कहता है कि some paramagnetic materials are aluminum, sodium, calcium, oxygen at FTP at the copper and the copper chloride. For a paramagnetic material, both chi and mu are depend not only on the material but also in a simpler fashion on the sample temperature. As the field increases or the temperature is lowered, the magnetization increases until it reaches the saturation value, at which the point all the dipoles are perfectly aligned with the field. फिर आता है फेरोमैग्नेटिज्म। यहाँ पर दिया रैंडमली ओरिएंटेड डोमेन्स और एलाइजेंट डोमेन्स का दिखाए हुए। फिर आता है फेरोमैग्नेटिज्म। तो ferromagnetism substances are those which get so strongly magnetized when placed in a external magnetic field. They have strong tendency to move from a region of the big magnetic field to a strong magnetic field. That means they get strongly attracted to a magnet. The individual atoms or the ions in the ferromagnetic material possess a dipole moment as in a paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called a domain. The explanation of this cooperative effect requires quantum mechanics and is beyond the scope of this textbook. Each domain has a net magnetization. Typical domain size is 1 mm and the domain contains about 10 power 11 atoms. In the first instance, the magnetization varies randomly from domain to domain and there is no bulk magnetization. This is shown in the figure 5.8a. When you apply Newton's magnetic field B naught, the domains orient themselves in the directions of the B naught and simultaneously the domain orient in the directions of the B naught grow in the phi. The existence of the domains and their motion in the B naught are not a speculation. One may observe this under a microscope after sprinkling a liquid suspension of the powdered ferromagnetic substance of the sample. This motion of the suspension can be observed. Figure 5.8 before the fusion when the domains have aligned and amalgamated to form a single giant domain. फिर आता है कि thus in the ferromagnetic material, the field lines are highly concentrated in non-uniform magnetic field. The samples tend to move towards the region of the high field, being bounded as to what happens when the external field is removed. In some ferromagnetic materials, the magnetization persists. Such materials are called the hard magnetic materials or the hard ferromagnets, as alnico, an alloy of the iron, aluminium, nickel, cobalt, and the copper is one such material. The naturally occurring lodestone is another. Such materials form the permanent magnets to be used among the other things as a compass needle. On the other hand, there is a class of the ferromagnetic materials in which the ferromagnetization disappear or removal on the external field. Soft and ion such material. Appropriately enough, such materials are called as the soft ferromagnetic material. There are a number of the elements which are ferromagnetic: iron, cobalt, nickel, gadolinium, etc. The relative अब ये सब है तो हम तो बिल्कुल ही यहाँ से जो स्टेटमेंट बना के पूछ सकते थे पॉइंट वाइज या फिर एक या ऐसे कर सकते थे बीच ऑफ द फ्लोइंग स्टेटमेंट इज ट्रू. इस प्रकार से तो हम पक्का यहाँ से फ्रेम कर देते. The ferromagnetic property depends on the temperature. At high enough temperature, a ferromagnet becomes a paramagnet. The domain of structure interferes with the temperature. The difference of the parameterization with the temperature is gradual. इधर से तो पक्का है जो स्टेटमेंट कितना ही फ्रेम कर सकते हैं और उनको ट्रू या करेक्ट या इनकरेक्ट करके ऐसे पूछ सकते हैं. नेक्स्ट है कि द समरी में कुछ है कि द साइंस ऑफ द मैग्नेटिज्म इज ओल्ड. इट हैज बीन नोन सिंस एंशिएंट टाइम्स दैट मैग्नेटिक मटेरियल्स टेंड टू पॉइंट इन द नॉर्थ साउथ डायरेक्शन like the magnetic poles repel and unlike ones attract, and cutting a bar magnet in the two lead to a smaller magnet. Magnetic poles cannot be isolated. When the bar magnet of the dipole moment M is placed in uniform magnetic field B, the force on it is 0, the torque on it is m cross p, the potential energy is minus m dot b, where we choose the energy of the energy orientation when m is perpendicular to the B. Consider a bar magnet of the size L and magnetic moment m at a distance r from the midpoint where r is much greater than L. The magnetic field B due to this bar is B is equal to mu naught m by 2 pi rq along the axis or minus mu naught m by 4 pi q along the equator. Gauss law for the magnetism states that the net magnetic flux through the enclosed surface is 0, यानी B delta F is equal to 0. Consider a material placed in external magnetic field B naught. The magnetic intensity defined as H is equal to B naught by mu naught. The magnetization M of the material in its dipole moment per unit volume. The magnetic field B in the material is equal to B is equal to mu naught H plus M. For a linear material, M is equal to chi into H, so that B is equal to mu naught H and chi is called the magnetic susceptibility of the material. The three quantity chi, the relative magnetic permeability mu r, and the magnetic susceptibility mu are detailed as follow. Mu is equal to mu naught into mu r, or mu r is equal to 1 plus chi. Magnetic materials are broadly classified as diamagnetic, paramagnetic, and the ferromagnetic. For the diamagnetic materials, chi is negative and the small, and for paramagnetic material, it is positive and the small. Ferromagnetic materials have large chi and are characterized by the non-linear relation between B and H. Substances which are at a room temperature retain their ferromagnetic material property for a long period, and a term come the permanent magnets. अब यहाँ पर दिया प्रोबेबिलिटी ऑफ द फ्री स्पेस होता है म्यू नॉट और डायमेंशन होता है m (L - -2 और यूनिट होगा टी एम ए -1 और रिमार्क होगा म्यू नॉट 4 पाई q इसके ऊपर -7. मैग्नेटिक फील्ड, मैग्नेटिक इंडक्शन और मैग्नेटिक फ्लक्स डेंसिटी बी वेक्टर है और इसका डायमेंशन होता है mt -2 और a -1. फिर इसका आ जाएगा टेस्ला और ये इंपॉर्टेंट है कि एक टेस्ला इक्वल टू होता है 10 के पावर 4 को. मैग्नेटिक मोमेंट का m होता है वेक्टर, स्मॉल m है वेक्टर है, L -2a डायमेंशन है और एम्पियर मीटर स्क्वायर इसका यूनिट है. मैग्नेटिक फ्लक्स इधर से मैचिंग का तो कर सकता है, मैचिंग बिल्कुल नहीं पूछ सकता है, इसको उठा के भी पूछ सकता है. मैग्नेटाइजेशन m का वेक्टर है L -1a एम्पियर पर मीटर और मैग्नेटिक मोमेंट बाय वॉल्यूम है. मैग्नेटिक इंटेंसिटी मैग्नेटिक फील्ड स्ट्रेंथ H वेक्टर है, L-1 A और एम्पियर पर मीटर, B इक्वल टू म्यू नॉट H प्लस M है। मैग्नेटिक सस्पेक्टिविटी का स्केलर है, M का इंटू H और रेडिएटिव मैग्नेटिक परमिटिविटी म्यू आर इक्वल स्केलर है, B इक्वल टू म्यू नॉट म्यू आर इंटू H और मैग्नेटिक सस्पेक्टिव म्यू इक्वल स्केलर है, ML T-2 A-2 और टेस्ला TM A-1 और N M-1 म्यू इक्वल टू म्यू नॉट म्यू आर और म्यू इक्वल टू म्यू इंटू H है। अब कुछ इसमें है कि points to ponder a satisfactory understanding of the magnetic phenomena in terms of the moving charge current current by a rapid rate after AD, but technological exploitation for the directional property of the magnet predict this scientific understanding by 2000 year. The scientific understanding is not a necessary condition for engineering application. Ideally, science and engineering go in hand, and one leading and affecting the other in the tandem. Magnetic monopoles do not exist. If you slice a magnet in half, you get two smaller magnets. On the other hand, isolated positive negative charge exists. These exist as a smallest unit of the charge. For example, the electronic charge with the value mod of is equal to 1.6 minus 19 coulomb. All other charges are integer multiple, and this is smallest unit charge. In other words, charge is quantized. We do not know why magnetic monopoles do not exist or why electric charge is quantized. A consequence of the fact that magnetic monopoles do not exist is that the magnetic field lines are continuous and form closed loop. In contrast, electrostatic lines of force begin on the positive charge and terminate on the negative charge or fade out at infinity. A minuscule difference of the value of the chi, the magnetic susceptibility, yields radically different behavior. Diamagnetic versus paramagnetic. For diamagnetic material, chi is equal to minus 10⁻⁵ and chi is equal to plus 10⁻⁵ for paramagnetic material. फिर आता है कि there is used a perfect diamagnet, namely a superconductor. This is metal at very low temperature. In this case, chi is equal to -1, mu r equal to 0, mu is equal to 0. The external magnetic field is totally expelled. Definitely, this material is also a perfect conductor. However, there is no classical theory which ties these two properties together. A quantum mechanical theory by Bardeen, Cooper, and the Schrieffer BCS theory explain this effect. The BCS theory by proposed in 1951 was eventually was the prize in the 1970. Diamagnetism is universal. It is present in all materials, but it is big and hard to detect if the substance is para or ferromagnetic. We have classified materials such as diamagnetic, paramagnetic, and the ferromagnetic. However, there exist additional type of the magnetic material such as the ferrimagnetic, antiferromagnetic, spin glass, etc. with properties which are exotic and mysterious. अब यहाँ पर कुछ क्वेश्चन है तो वो देख लेते हैं. तो क्वेश्चन पहला क्वेश्चन है कि शॉर्ट बार मैग्नेट प्लेस्ड इन ए विद एक्सिस एट 30 डिग्री बिटवीन द फॉर्म एक्सटर्नल मैग्नेटिक फील्ड ऑफ द 0.25 टेस्ला एक्सपेरिमेंट टॉर्क ऑफ मैग्नीट्यूड इक्वल टू 4.5 × 10⁻⁴ जूल. तो व्हाट इज द मैग्नीट्यूड ऑफ द मैग्नेटिक मोमेंट ऑफ द मैग्नेट. मैग्नेटिक फील्ड स्ट्रेंथ B इक्वल टू 0.25 टेस्ला दिया हुआ है. टॉर्क ऑन द मैग्नेट T इक्वल टू 4.5 × 10⁻⁴ टेस्ला दिया हुआ है. एंगल between the bar magnet external field theta equal to 30 degree. तो टॉर्क इज इक्वल टू एम बी साइन थीटा, एम इज इक्वल टू टी बाई बी साइन थीटा. तो 0.36 जूल पर टेस्ला आता है. तो मैग्नेटिक मोमेंट ऑफ द मैग्नेट आएगा 0.36 जूल पर टेस्ला. फिर आता है कि शॉर्ट बार मैग्नेट ऑफ द मैग्नेटिक मोमेंट m इक्वल टू 0.32 जूल पर टेस्ला is placed in the form magnetic field of 0.15 tesla. If the bar is to free to rotate in the plane of the field, which orientation would correspond to its stable and unstable equilibrium, what is the potential energy of the magnet in each case? तो मोमेंट ऑफ द बार मैग्नेट होता है m इक्वल टू 0.32 जूल पर टेस्ला और एक्सटर्नल मैग्नेटिक फील्ड B इक्वल टू 0.15 टेस्ला है. तो द bar magnet lies along the magnetic field. The system is considering as being in a stable equilibrium. Hence, the angle theta between the bar magnet and the magnetic field is 0 degree. Potential energy of the system minus mb cos theta यानी माइनस 0.32 गुना 0.1 cos 0 यानी माइनस 4.8 गुना 10⁻⁻² जूल. फिर आता है कि the bar magnet is oriented 180 degree to the magnetic field. Hence, it is unstable equilibrium. तो theta is equal to 180 degree. Potential energy is equal to minus mb cos theta यानी 4.8 गुना 10⁻² जूल है जो आ जाता है. अगला सवाल. A closely wound solenoid of the earth returns an area of the cross section 2.5 गुना 10⁻⁴ meter square carries a current of 3 ampere. Explain the sense in which the solenoid act like a bar magnet, but its associated magnetic moment. तो नंबर ऑफ टर्न्स इन द solenoid दिया है 800. एरिया ऑफ द क्रॉस सेक्शन 2.5 गुना 10⁻⁴ meter square. Current in the solenoid I equal to 3 ampere. तो एक current carrying solenoid behave as a bar magnet because a magnetic field develops along its axis along its path. The magnetic moment associated with the given current carrying solenoid is calculated m is equal to NIA. तो 0.6 जूल पर टेस्ला इसका आंसर आ जाएगा. अगला सवाल. If the solenoid in exercise 5.5 is free to turn about the vertical direction and in the form horizontal magnetic field 0.25 tesla is applied, then what is the magnitude of the torque on the solenoid when its axis make an angle of 30 degree with the direction of the applied field? तो magnetic field strength दिया 0.25 tesla, magnetic moment 0.6 m is equal to दिया 0.6 टिफ्ला इन्वर्स. The angle theta between the axis of the solenoid and the axis of the solenoid applied angle 30 degree. Therefore, the torque acting on the solenoid given by tau is equal to mv sin theta. तो 7.5 × 10⁻2 जूल आ जाएगा. फिर आता है a bar magnet of the magnetic moment 1.5 joule per Tesla lies along the direction of uniform magnetic field of 0.22 Tesla. तो what is the amount of the work required by external torque to return the magnet for it to realize its magnetic moment? Normal to the field direction, opposite to the field direction, or what is the torque on the magnet in the case of the 1 and the 2. तो magnetic moment में जो है 1.5 joule per Tesla और magnetic field strength B is equal to 0.22 Tesla. Initial angle between the axis and the magnetic field theta 1 by 0 degree और final angle between the axis and the magnetic field theta 2 by 90 degree. The work required to make the magnetic moment normal to the direction of magnetic field given by minus mb cos theta 2 minus cos theta 1 यानी minus 0.33 joule. तो initial angle between the axis and the magnetic field theta 1 by 0 degree और final angle between the axis and the magnetic field theta 2 बराबर आता है 180 degree. तो the work required to make the magnetic moment opposite to the direction of the magnetic field given to W is equal to minus mb cos theta 2 minus cos theta 1 यानी 0.66 joule. For the case theta 1 is equal to 90 degree, torque is equal to mb sin theta और 0.33 जूल आता है. थीटा इक्वल टू 180 डिग्री, टॉर्क इज इक्वल टू mb sin थीटा और mb sin 180 डिग्री यानी 0 जूल आ जाएगा. नेक्स्ट क्वेश्चन. A closely bound solenoid of 2000 tons and area of cross section 1.04 meter square carrying a current of 4 ampere is suspended to its center along it to turn in the horizontal plane. What is the magnetic moment associated with the solenoid? फिर आता है what is the force and the torque on the solenoid in uniform horizontal magnetic field of the 7.5 Tesla is set up at an angle of 30 degree with the axis of the solenoid. तो नंबर ऑफ टर्न्स ऑफ solenoid n बराबर 2000 है. एरिया ऑफ द क्रॉस सेक्शन ऑफ solenoid एरिया 1.4 मीटर स्क्वायर है और करंट ऑफ solenoid 4 एम्पियर है. तो मैग्नेटिक मोमेंट अलोंग द एक्सिस ऑफ द solenoid कैलकुलेट है एन आई ए. तो 2000 गुना 1.5 यानी 1.28 एम्पियर मीटर स्क्वायर. मैग्नेटिक फील्ड बी इक्वल टू 1.5 × 2 टेस्ला. तो एंगल बिटवीन द मैग्नेटिक फील्ड एंड एक्सिस ऑफ solenoid होता है थीटा इक्वल टू 30 डिग्री, टॉ इक्वल टू mb sin थीटा. तो बी एच इक्वल टू बी कॉस डेल्टा. तो बी इक्वल टू बी एच बाई कॉस डेल्टा यानी कि 0.32 जी गॉफ आ जाता है. तो Earth's magnetic field lies in the vertical plane 12 degree west of the geographic meridian making an angle of 60 degree apart with the horizontal axis its magnitude 0.32 gauss. अगला क्वेश्चन है कि a 40 bar magnet has a magnetic moment of 0.48 joule per Tesla. Give the direction and the magnitude of the magnetic field produced by the bar magnet at a distance of 10 cm from the center of the magnet on the axis on the equatorial length of the magnet. तो magnetic moment of the bar magnet दिया हुआ है 0.48 joule per Tesla. डिस्टेंस d बराबर 0.1 मीटर. तो magnetic field at a distance d from the center of the magnet on the axis given by μ0/4 by 2m/dq. तो यहाँ से निकालेंगे तो 0.96 g आ रहा है. μ0 permittivity of the free space है 4 पाई गुना 10⁻⁴ टेस्ला मीटर पर एम्पियर. द मैग्नेटिक फील्ड इज लॉन्ग द फोर्थ नॉट डायरेक्शन आ जाता है. फिर है द मैग्नेटिक फील्ड एट ए डिफरेंस 10 सेंटीमीटर d बराबर 0.1 मीटर ऑन द इक्वेटोरियल लाइन ऑफ द मैग्नेट गिवन बाय. तो b इक्वल टू μ0/4 पाई m/dq. तो यहाँ पर 0.48 गॉस आ जाता है. तो मैग्नेटिक फील्ड इज लॉन्ग द नॉर्थ साउथ डायरेक्शन है जो आ जाएगा. तो यहाँ पर मैग्नेटिज्म का चैप्टर है जो कंप्लीट होता है. इससे एनसीईआरटी है जो इसका एनसीईआरटी काफ़ी इंपॉर्टेंट है.